Hey guys! Oh, another wonderful edition of Patio Productions for Pre-Calculus coming your way. Today we are going to be dabbling in section 16-2. We are going to take a whopping 3 days to get through section 16-2. So that'll take us to the end of the week. And so we're going to do it in manageable chunks and have nice little manageable pieces of homework. So let's get started. Okay, so we have talked about already limits. Okay, so we've talked about limits. We've talked about like how to do limits, how to find them. And so we're going to talk about them a little bit more, but we're going to talk specifically about some rules for limits. Okay, so today's topic is going to be on limit theorems. And we're going to talk about doing it sort of a little bit painfully. And then we're going to talk about a streamlined way to do it. Yeah, I know you're going to be excited about that. And then let's get started. Okay, so limit theorems. Okay, so there are some theorems that allow us to calculate limits quickly. And we sort of like divided them up into like two bunches. Okay, so this first bunch of limit theorems is just two of them. Okay, two lovely limit theorems, and it goes like this. And guys, I do want you to write these down because the notation is important. Part of being a good mathematician, right? We talk about being a good mathematician, right? I know, they're so amazing, is that we want to be able to like absorb notation and roll with it and look at it. Okay, so this says if f of x is equal to a constant k, so like 5, 7, 1/3, -2, so anything that's a constant, then the limit as x approaches c of f of x is just equal to k. So let me get my pin going here, right? If this guy right here happens to be just a k value, like a number k, then the limit is that number. Easy cheesy, done. Okay. Basically, we would say the limit of a constant is a constant. If we were in class, I would have us chant that. The limit of a constant is the constant. Go ahead and repeat it after me. So I'll say it and then you say it. The limit of a constant is a constant. Your turn. The limit of a constant is a constant. Good job, guys. Excellent work. Okay. The next little theorem that we're going to talk about is if f of x is some sort of x to a power. Okay, so m is going to be a positive real number. And so if f of x is equal to x to the m, where m is a positive real number, then we can say the limit as x approaches c of x to the m is equal to c to the m. Yay! Look at that. So nice and pretty. Okay, so the limit as x approaches c of x to the m is going to just be c to the m. Okay, we kind of did this in our previous lesson where you just sort of like plugged in the number. So the limit of x to a power is that number to that power. The limit of x to a power is the number to the power. Repeat after me. The limit of a number is the, JK, whoopsies, messed that up. Let's do that again. The limit of x to a power is the number to the power. Your turn. The limit of x to a power is the number to the power. Good job, guys. Excellent work. Okay, so let's do this 2 truths and a lie style. So when we do 2 truths and a lie, you're going to write down all the questions. And I'm going to give you 30 seconds to figure it out. I will do 2 drum rolls, maybe 3 drum rolls, and then we'll decide which one is the lie. So part A says, the limit as x approaches 3 of 10 is 10. Part B, the limit as x approaches -3 of x to the 3rd is 27. Part C, the limit as x approaches 2 of x to the 5th equals 32. You have approximately 2 or 3 drum rolls to figure this out. Go. Third drum roll. Okay, I'm sure that was just plenty enough time for you guys to figure this out. Did you figure out that part A was correct? Did you figure out that part C was correct, but part B? That was the lie. Okay, for part A, folks, the limit of a constant is the constant. So even though this number says x is approaching 3, 10 is a constant, folks. The answer is just going to be 10. Check mark, it works. On part C, it says as x approaches 2 of x to the fifth. So you just take that 2, plug it in, go 2 to the fifth, and you get 32. But part B was wrong. That's because it was supposed to be negative 27. So I feel like I know what they did. They just accidentally forgot the negative right here. Whoops-a-daisies. But the answer should be negative 27. Excellent work, guys. Excellent work. Okay, so if we know these 2 basic rules, we can combine those rules to get more intricate functions and utilize this next set of rules. I know there's a whole nother set of rules coming up, okay? So I'm going to be honest with you guys, right? It's going to look wordy. They're going to look wordy, but we're not going to be afraid by it. We're going to be like this. Bring it on, right? The notation is not going to bother me. We're going to write it down. So I'm going to go nice and slow. We're going to write down the rules. If I go too fast, just pause the video. Here we go. Okay, so limit theorems part 2. If you have, this is the setup. If you know that the limit as x approaches c of f of x is equal to capital L, and then you know the limit as x approaches c of function g of x equals m, and those both exist, then we can get some rules. Okay, I want you to notice something. This says as x approaches c, this says as x approaches c. So we're approaching the same number. This is an f of x function, this is a g of x function, and then we have like 2 different answers for those limit equations. Then here's what we get. Okay, one of the rules says that if you take the limit as x approaches c of the a sum of f of x plus g of x, that would actually just equal, you could almost like split up the limit. You're not distributing the limit, but you're almost like making the limit go to each part, which is kind of like distributing. I know. It's like the same thing. Okay. You can say the limit is x approaches c of f of x plus the limit as x approaches c of g of x. And then each of these individually have an answer. So it's just L plus M. That's it. Very nice. Okay. You would say it like this. The limit of a sum is the sum of the limits. Okay. The limit of a sum is the sum of the limits. Your turn. The limit of a sum is the sum of the limits. Good job. Good job. Excellent. So glad you're in class participating. Okay. The next guy is going to look almost exactly the same as this one, but instead it's going to have a minus instead of a plus. So this guy is about the difference. So we're going to say the limit as x approaches c of the difference f of x minus g of x. That would be equivalent to the limit as x approaches c of f of x minus the limit as x approaches c of g of x, and that would be capital L minus capital M. We would say in English that the limit of a difference is the difference of the limits. Oh, so great. Okay, I'm going to say it one more time. You're going to repeat after me. The limit of a difference is the difference of the limits. Your turn. The limit of a difference is the difference of the limits. Good job, guys. Excellent. Repeating back after me. Okay, we have now the multiplication version of this. Oh my goodness, it seems to be so repetitive. I'm so excited. So this says the limit as x approaches c of f of x times g of x is going to be the limit as x approaches c of f of x times the limit as x approaches c of g of x, and that would be the limit L times the limit M. Very nice. So fun. And so we would say now the limit of a product is the product of the limits. Okay, I'm going to say it once, then you say it after me. The limit of a product is the product of the limits. Your turn. The limit of a product is the product of the limits. Good job. Okay, our fourth rule is the division version of this guy. So this is going to say the limit as x approaches c of f of x divided by g of x is technically the same thing as the limit as x approaches c of f of x divided by the limit as x approaches c, excuse me, of g of x, which would be capital L over capital M, as long as M is not equal to 0. And then we say, I got all choked up about this one, guys. Excuse me. The limits, they're just so beautiful. I just couldn't help myself. We're going to say the limit of a quotient is the quotient of the limits. Okay, your turn. Limit of quotient is the quotient of the limits. Excellent job. Okay. All of this right here, I'm going to be honest with you. All of this, so wordy, so crazy. I can't even believe it. You're like, there's so many terms. It's way easier than you think it is. It really is. Okay, let's do some of these with some examples, and you're going to be like, this is amazing, Mrs. Fox. This is what you're going to say. So these theorems are going to make it easier for us to evaluate something like this, okay? So consider this as an example. The limit as x approaches 2 of x squared plus 3x minus 5. If we really and truly wanted to evaluate this limit, this is what we would have to do, okay? This is really what we would do. We'd say, okay, the limit as x approaches 2 of x squared plus 3x minus 5. This limit would be treated to like every single little piece, right? This limit would apply to this guy. This limit would apply to this guy, which was actually its own product. And then the limit would apply to this guy. So it's going to be something like this. It would be the limit as x approaches 2 of x squared plus the quantity, the limit as x approaches 2 of 3, times the limit as x approaches 2 of x, minus the limit as x approaches 2 of 5. And then we would evaluate all these little pieces. So according to our first set of rules, the limit of x approaches 2 of a number to a power is you just put the number to a power. So it would be 2 squared. Then you would have the limit as x approaches 2 of 3, but 3 is a constant, so it would just be 3. And then the limit as x approaches 2, this would be like x to the first power, so that would be a 2. And then we would minus the limit as x approaches 2 of 5, but 5 is a constant, and then we would go minus 5. Guys, seriously, I feel like this. That was a lot of writing, and I'm not even done with the question yet. I still have to algebraically figure it out. That 2 squared turns into a 4, the 3 times the 2 is a 6, and then we go minus 5, and then finally we combine all these things, and we get a positive 5 for the answer. Okay, that is so much writing. So much writing. Like, seriously, I am out. I'm like this. Seriously, bleh. This is gross. I do not want to do that again. So instead, we have the limit rules. We are never, ever, 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 ever going to write this again. That is too much writing, you guys. Ick. Instead, we just go straight to substituting, okay? Because the limit of a sum is the sum of the limits, because the limit of a product is the product of the limits, we just get to straight plug it in and call it a day, okay? So if we were going to answer a question like the limit as x approaches 2 of x squared plus 3x plus 5, minus 5, you literally just take this 2 and plug it into every time you see the x and call it a day, okay? So nice and pretty. So it just becomes 2 squared plus 3 times 2 minus 5, and then lickety split fast. No extra writing, no writing the limit 4 times. That is nonsense. It just becomes just a 5. The end. Have a nice day. Oh, so much better. So much cleaner, so much nicer. That's all you're going to do. So whenever they ask you to take the limit as it approaches a number, basically you just get to plug in the values. Let's do some real examples. This guy says, for example, number 2, find the limit as x approaches 4. So the limit as x approaches 4 of x squared plus 5 over x squared minus 2x. Folks, we are not going to split this up into like 4 different limits and not at all. We're just going to take this value of 4 right here, and plug it in every time we see an x. So this becomes a 4 squared plus a 5 over a 4 squared minus a 2 times a 4. And on the top, that's a 16 and a 5, and that makes like 21. And then on the bottom, we've got a 16 minus 8, and that makes like an 8. And so the answer, is 21/8. That's it. That's all you have to do. So simple, so clean. Okay? So, do you remember, I think that we did this when did we do this? Yes, we did this when we did series. Yes. And so it was a little bit like clunky because we weren't like professionals at limits yet, but we're starting to become professionals now. And so do you remember that when we did the limit as x approaches infinity or negative infinity, when you have like a number, like it doesn't even have to be a 1, but like this is a number over x, that this number just gets like really, really big, and this number gets like really, really big, but negative style, that basically these just turn into 0. Okay, that's a really fun fact for us, okay? So this helps us evaluate limits that go to positive or negative infinity, okay? So when we do our limit, it's going to say as x approaches, and then it's going to be an infinity symbol. So this is not going to be a number this time where we could simply like plop, 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 plug it in. Yeah, that would be the last rule. Now we're going to go to positive or negative infinity, okay? So we're going to do a couple of examples here. So this says find the limit. So you'll notice this is a different type of question. This says as x approaches infinity. This says the limit as x approaches infinity of x squared plus 7x all over 3x squared minus 2. you can't plug in infinity. That doesn't like make any sense. Infinity is more like a concept instead of a number. And before we were talking about like plugging in numbers. So you're like, oh, that's tricky on this one. So instead, what we're going to do, if you remember this process from when we did the series and sequence chapter, you're going to evaluate this guy algebraically. Okay, we're going to try to get some 1 over x's or 1 over x squared, something like that. So if you want, you can divide the top and the bottom of a fraction by the same thing, and that is perfectly legal mathematically. Yeah, it is. I'm going to choose an x squared. Okay, so I'm going to choose an x squared to divide the top and the bottom by. And so for my next step, I'm going to write, it's still the limit. Notice that I'm still writing this limit notation. The limit as x approaches infinity. I'm just changing how this looks. So this becomes an x squared over an x squared, because this is going to go to here, divided in, and x squared over x squared is 1. Then when I do it to here, 7x over x squared simplifies to be 7 over x. I'll do that to this guy right here. 3x squared divided by x squared is just a 3. And then to this guy, a negative 2 divided by x squared is a negative 2 over x squared. Okay, now if we plug in infinity now, right, like thinking about like this concept, 7 over a really big number, boom, it's going to go to 0. 2 over a really, really big number is also going to go to 0. And so all that's left is a 1 and a 3. And just like that, we have a beautiful answer of 1/3. Isn't that nice? Okay, so doing that algebraic technique by dividing by like one of the x to the squared or an x cubed or even an x is an amazing way to simplify our guys. Let's do a part B example. This guy says the limit as x approaches negative infinity. Oh, that doesn't matter that it's negative infinity. No big deal. Of x squared minus 5 all over 4x cubed plus 2. So we're not really like plugging in infinity, but we do need to think about something where we can like evaluate it. So in this case, I think I am again going to divide the top and the bottom by an x cubed this time. Okay, so I'm going to try an x cubed. I actually think it would work perfectly well by doing it with an x squared also. So it's just style choice. So we're going to do this guy to this and here, and then this x cubed to here and here. We're going to see what we can come up with. So again, we're still writing the limit as x approaches negative infinity. If we do x squared divided by x cubed, I get a 1 over x. A 5 divided by x cubed would be minus now 5 over x cubed. Over here, I get a 4. So 4x cubed divided by x cubed is just 4. And then plus a 2 divided by x cubed. Several of these are going to go to 0 if we take the limit as x approaches negative infinity. This 1 over x would be 1 over a really big number, gone. So this is going to go to a 0. This guy is going to go to a 0. This guy is going to go to a 0. And all that I'm left with now is a 0 minus 0 over a 4 minus 0, which would be a 0 over 4, but 0 divided by anything is 0. Wouldn't you look at that? That's how we can do it. Ladies and gentlemen, great algebraic strategies. So what we learned today is how to do things algebraically very cleanly, okay? So, and then we learned about things when we're going to positive or negative infinity. You have like a whopping 12 questions for homework. Like, seriously, I can't make it any easier. Remember, we're doing this in bite-sized little bitty chunks so that your brain is not imploding. I know that you have lots of other things that you're doing in other classes. You're ramping up for your APs coming up like next week or the week after. So manageable chunks. Stay on top of this, you guys, okay? So your homework is going to be page 863. You're just going to do 1 through 9 and 14 through 16. That's all you guys are going to do. Okay, let's go ahead then and get back to our presentation. My face, oh, there I am. I'm back. Okay, ladies and gents, I hope that was an excellent lesson. You're going to feel very prepared to do your 12 questions of homework. I'm guessing it's going to take you so much less time than it was to watch this video. I think you guys are going to be in good shape. Let's do our fanfare music to get us out of here. Another edition of Patio Productions done. Bye, guys. See ya.